And similarly, we just extended it for the for the steam as well. We do for hydrogen and CO earlier without assuming no steam co-production, but now we have steam as well, and that's how we do the same. Look at the jump pole head, and that's what they call energy transition. Within 10 years, 20 years, 30 years, we suddenly move from one source to another source. That was the first one, and the next one came somewhere around this period when the oil was discovered. This was the first one with coal, and then suddenly somewhere around 1910, oil once again was discovered much earlier, but it was not started as a major energy source until early 1900s. Then here also you could see how this color is for oil, how this should work during this period. That was the second energy transition. Now we are witnessing, we are today talking about actually in reality the third energy transition, but most of the people think it's a new term, energy transition. I think we saw this slide earlier, no, not yet. And we saw some issues associated with the carbon intensive fuels. Here on this slide you can see the deaths associated with the air pollution using different energy sources. Once again, the area of the triangle is absolutely no that's the electricity produced, that's per unit of electricity. So coal, as you all know, it's not only CO2. CO2 is GWP, global warming potential, but burning coal also results into several other pollutants like SOx, NOx, particulate matter. So as you go cleaner, it's also safer, you can say safer or healthier. This we already saw. So need of the day or call of the day is to go from higher C2X ratio to low to CX ratio. On this end we have infinity, on this end we have almost zero. I'll skip this slide. We already saw where this energy is coming from. Still coal is share between the gas and the remaining oil and some other sources. And you could see the renewable or the clean energy sources still doesn't make up so much in the complete energy mix. Yeah, electricity. So we said where this CO2 emission is coming from, majority is from electricity. That's all about electricity. Everybody thinks that electricity was discovered somewhere into 1800s. Inherent advantage, transferred by a cable. There's no transfer of material, and it suddenly took over huge amount of energy production, energy use after its invention. So once again we'll look into the current electricity generation. So this we already talked about. We burn fuel in the boiler. It's the simplest form of power plant. We burn fuel in the boiler. Can somebody tell me why we cannot have, why do we have to condense the steam after the turbine? So we have steam here, steam is coming out, and then we condense it somewhere here. So normally, a lot of energy content of steam is basically from its latent heat. So we can see nature for 1 kg for atmospheric pressure, it is somewhere around 2100 kJ/s. But if you start condensing steam in the turbine, sudden phase change will damage the blades. And we still do not have an electricity which can support condensation of steam inside. So, although steam has very good properties, it's non-toxic, non-flammable, non-corrosive, and can carry a lot of energy. So energy density is very high. You can put in a lot of energy in 1 kg of steam or water. That's a typical, just wanted to show a typical thermal power plant, how you produce it, the electricity. So some mass balance and energy balance calculation, we put in 30 megawatt fuel based on LHV. Only 12 megawatt is coming out.
ऑडियो इसमें ले रहा है कैमरा वहाँ से
Maximum amount of energy content of the steam is
ऑडियो के लिए चालू कर
phase change.
राइट
And if we are not changing the phase, we are losing a lot of energy. You cannot have this steam going back to the boiler. So you have to condense it and then generate once again the steam. So a lot of energy is lost here in this condenser. So basically you flow cooling water inside the condenser, and then ultimately this cooling water, as I said, goes to the cooling tower. Energy is lost to the atmosphere. Another energy loss will be you burn your fuel, but you can extract energy from this flue gas up to a certain point. So let's say, for an example, 170, 180 degrees. So that's the amount of stack losses. So there are two losses here. So one is here and one here going to the cooling tower. So typical, just wanted to give feeling and typical numbers for power generation using coal. So as we said, maximum amount of energy content of the steam is in its latent heat, and we already agreed, or we already said, we cannot condense it within the turbine. But what we can do, if we generate steam at higher temperature, so let's say this energy content of the steam going to the turbine is high, then probably fractionally we can reduce the losses. So we transfer more energy at higher temperature, and that's what I'm showing here. So this is what goes into the turbine. Let's say this is the base case, and this is what comes out of the turbine, and the liquid fraction is 1. Typically flue gas come in and out, it's somewhere around 93, the efficiency. That means when I say 93% is what goes here as the fuel LHV, and minus what comes out, this is what is going to the turbine. That's something else, what you are using from the turbine, that's something else. But just purely on the flue gas side, you can have 92, 93% efficiency. So here, in this example, you could see 30 as the fuel value we are putting in, and 3 is lost, so efficiency is 90%. Just from this point to this point. But out of this 90, we are only using 50 here. Is it 50? No, even lower. So 27 is coming in, 15 is a little bit higher than 50. Ultimately 12 divided 30, that's the 40% efficiency. So just to give some feeling how you can optimize it, how you can increase the efficiency. Always, for all the cases, let's say flue gas in, out, I'm with 93% efficiency. Base case, I generate steam at whatever temperature, whatever pressure, but I superheat it up to 400 degree. I'm coming out at 110 degree. Liquid fraction is 1. Steam turbine in and out, that means it's 90%. But as we said, we cannot have liquid fraction 1 from the turbine. We cannot have condensation within the turbine. So that's not the reality. But just to give you feeling, one way of increasing efficiency would be if I can reduce the temperature at the outlet of the turbine. So if I go from 110 to 70, that means within the turbine I am extracting more energy. That can increase my efficiency in the turbine. Efficiency will go up. But this variation is just to show effect of this variation, right? These two places. But reality is this: we cannot have condensation, so the liquid fraction coming out from the turbine will be 0, right? And then look at the efficiency, overall efficiency, 42%, because within the turbine we are only extracting 45%, right? How we can optimize it? So as we said, we reduce the energy of the energy content of the steam coming out of the turbine, but we are at 70 degrees. So what's the boiling point of water at 1 bar? Sorry, 100 degree. So 70 degree, it means we are already under vacuum, right? And here, but there is a limit. Another way is you put in more energy at the inlet. So you go at 500, 600, here you could see efficiency is going up. So this one stays same. We assume flue gas is coming out at the same temperature from the stack, and we are just varying here this superheated steam temperature. So the same So what we are doing here, we are burning fuel. Chemical energy of fuel is transferred to the thermal energy, to the steam. But what we can do, instead of using fuel which contains a lot of carbon, we can use nuclear reactor and harness nuclear energy. So the whole rest of the whole cycle is similar. It's just the thermal energy supply medium is different. In earlier case, it was burning a carbon-containing fuel. Now it's the nuclear reactor. So there is another way of generating electrical energy is hydro. Hydro share in the overall electricity mix in India is a little bit higher than the global average, because we are blessed with a lot of rivers, and we are also blessed with advantageous terrain. You just you don't have to have rivers, but you also need to have terrain that you have some slope. Here you could see. I mean, basics of hydro generation everybody knows. But as I was saying, we are blessed with such a terrain that at certain 200, 300 meter we have higher level, and then at 200 meter later we have lower level, so that we can make use of this potential energy difference, make a dam, stop the water, and have the controlled flow of water from high level to low level. By this you turn the turbine and generate the electricity. So other two methods up to this point is similar. It's just the energy is not transferred by steam, but it's water, and it's not the thermal energy, but it's the potential energy. Now comes the sun. So global solar radiation, how much solar radiation we receive at ground level. So global average is somewhere around 1300 watt per meter square. But the problem with solar is it's not shining 24 hours a day, 7 days a week, 365 days a year. But if you have natural gas, you can burn it 365 days a year, 24 hours a day, 7 days a week. So it's continuous supply of energy. Extract natural gas and have continuous supply of energy. That's the problem with sun, solar energy. It's only, you could say the daily 12 hours of daylight, night time, but there is also a disparity between locations. Once again, in India we are blessed with more sunshine than some other countries. So if you go to Scandinavian countries like Norway, sun rises somewhere around 9 a.m. and it's already dark. It's only 6-7 hours. That's in winter. But we have year-round sunshine. But we have year-round sunshine, and some other countries like Middle Eastern countries, South American countries, they are also equally blessed. Some countries even better than us. So if you look at the potential, you could see the solar to electricity generation currently is somewhere around 20%. So the solar PVs what we have nowadays, the efficiency is somewhere around 20%. And a lot of research is focused on increasing the efficiency of solar PVs also. Now, if you look at the whole land mass we have, leave 70% for ocean, which is a good number. So only 0.4% of remaining land mass is required for total worldwide. Do some maths based on 1300 watt per meter square. And out of this remaining land, 0.4% land, if I leave 35% of forest land area also, only 0.6% is required to supply the energy demand of the whole world. Then there is wind. So we started with coal or natural gas, the steam cycle generated power, and went to the nuclear, hydro, solar. So we're just looking at each and every source of power generation. So that's wind. So we all know that the specific heat of soil is much lower than specific heat of water. It means, and God's sun is not distinguishing between sand, soil and water. So the solar radiation is similar. That means for the same amount of energy hitting the ground and hitting the water, the water will be, let's say, will be at lower temperature. So similarly, the temperature of the air over the water is lower, and that creates a density difference and a natural dark, which later on turns into what we see as wind. And this energy, this kinetic energy can also be harnessed. So once again, like hydro, it's the potential energy of the water due to the grade difference. This time is the kinetic energy of wind, which is used to turn the turbine and generate electricity. So there was another way of, or there is another way of harnessing the sun energy directly as thermal energy. So you generate steam via thermal energy absorbed from the sun, and once again turn the turbine to generate electricity. From the sun, the first one was about the thermal energy, but thanks to the invention of PVs or electromagnetism, you can directly convert the solar energy into electrical energy. That's the much efficient way of generating electricity from sun. So coming back to the first source, here we had the coal. Here we had coal. If we replace this coal with biomass, we could apply the same cycle and generate once again electricity via steam cycle. Okay, then there is another way of using biomass. Instead of having this thermal cycle, you can have the bioconversion to some fuels like bioethanol. You use biomass and convert into a suitable fuel like ethanol. I think this we already discussed. There are so many hurdles moving from conventional to away from conventional energy sources. So I think this we didn't talk about. Oil and coal-based power generation this society has been doing for last almost 100 years. And it's a very well established technology. Oil and coal still has abundant supply. There's a lot of reserves still available. So it's also once again the political aspect into this. To promote the green energy and to promote energy transition, people are saying we do not have oil left, but fact is there are still a lot of oil reserves and gas reserves left, even coal. So as we were talking before lunch, so societal inertia, personal inertia. There is also economy of inertia. So who will pay for this extra cost? I've been doing this for years, so I'll continue to do this. Difficult to convince people, society. Cost of power generation still favors oil, coal. We saw already the economics, 174 versus 79 euro per megawatt hour between natural gas and coal. So who will pay for this extra cost? Supply chain resources issue. So these are new technologies. That's true. Uncertain geopolitical environment. We are living in a world where we have so many fights going on, war going on. I think 50 years back there were more alignment, the governments were more aligned than today, so that's also. We touched upon the nuclear power. There are also, nuclear power is a very let's say, potential clean energy source, but there are so many risks associated with nuclear energy. Just to mention some of them, accident is a big thing. Japanese accident has really scared many governments, and most of European governments have already decided to shut down all their remaining nuclear plants. Okay, I think this we already saw in the morning. It's nothing new, but I wanted to cover that. So this we just started to talk about this disparity into solar energy available. So here you could see we are somewhere here, and in the region of 2,400 to 3,000 hours every year we have bright sunlight. And just compare this with this region, which is Europe, Northern Europe, some parts of Russia. You are even below 1,200 hours per year. So this is just to show the perspective. There is a disparity in solar energy available worldwide. Now let's do the calculation what we did in the morning for these two locations. For these two locations, one where we have 2,500 hours, 2,500 hours per year, like India or some other country, and on one location we have 1,200 hours per year. So capex of the solar panels is, for sake of simplicity, I assume similar. And as we were discussing in the morning, the capex, the money you spend, you have to pay it back. So we use normally a small factor, capex factor, 14%, that based on the rate of depreciation and the interest rate what you assume. But based on these assumptions, you could see that at one location, using the same energy source, I have the electricity price 174, on the other one 84. So huge dependency on the location. So one can say, okay, let's produce power at this location and transfer it to this location where you do not have so much sunshine. But the problem here is we have a lot of transmission and distribution losses. So it can add up to 8%. And this number is for a certain, if I remember correctly, some 1,500 kilometers or so. But as you go intercontinental or interstate, you can have almost 30-40% loss. So whatever you are generating at one point, almost 40% is lost before you receive it on your receiver end. And here you could see the transmission losses that depends also on the population density. So if you have high population density, you do not have to travel so much. So your losses are low. So high population density, lower losses. I don't see India here, but we are also somewhere in this region. So higher losses. So the one issue with the solar is disparity into solar radiation based on the location. Another one here you could see, and that's a major issue, over the daytime. And these are the plots showing energy consumption over the daytime, so from midnight till midnight. You could correlate it in the early morning hours, let's say until morning hours the energy consumption is very low and then it's slowly going up and then it stays, and in the evening times slowly going down, right? And that's the power production if you install a solar PV. So during this period you could see there is no solar power generation, but there is some consumption. And in this period you could see there is a lot of solar power production, but there is not so much consumption. So during the day, 0 to 24 hours, at certain point a time you are producing less or you are producing nothing, but at certain point of day you are producing much more than what is required. So that's also an issue with the solar energy, which we call normally intermittency issue. So this power is supplied not continuously like in natural gas based power plant. You can run it 24/7, 365 days a year. Here you can have power intermittently. So that's the intermittency issue what we have. Now how we can solve this problem is with hybrid solution. So what you can do, you can have a natural gas based power production and the solar PV based power production, right? So during this period when you do not have any solar power production, you turn on your natural gas power plant and generate power what is required. But what you will do with the additional power generated during this period, because you could see here you have much more power production than what is required, right? So here you could see we had the same natural gas based power plant. You have the fuel, the gas turbine, steam cycle together, and then you on the steam cycle you add the solar electricity, right? So we said when we do not have solar power, we can generate power via electricity, via natural gas, right? And during this period when we are generating more, we can store the energy in batteries, right? So this one is hybriding natural gas power plant, solar PV, and even the battery storage. So combining solar and say fossil-based power generation, so synchronization of supply-demand solution for intermittency problem. These are expensive. Well, you could imagine if we have only natural gas-based power production, you just install this much capex. But if we have hybrid solution, you have to install capex for solar power production, also for the natural gas-based power production. So of course your capex is much higher. So that's what we have here on point number 3, high capex compared to standalone NG-based power production. So reduced CO2 emission, pure solar means no emission, but during the time when you are running your NG-based power plant, you have some, so you can have from 0 to 1 with the pure solar-based power production up to pure natural gas-based power production, something in between based on the ratio of power supply between these two sources. Solving this intermittency issue using battery, that's also nowadays gaining momentum. But the problem with the battery is the loss of, let's say, it deteriorates the economics, so losses. And we are talking about losses not in terms of weeks or months, but in terms of hours. So whatever you store in your battery, you will not get the total power even next day. So full battery and solar power, that's I would say still far away. And a lot of research is focused also on increasing the efficiency of solar. So we saw at the moment it's somewhere around 20%, and you could imagine increasing it by 2%, you suddenly increase the power production by 10%. So 20 to 22, it's only 2% in terms of efficiency, but the power production will suddenly go 10% higher. So a lot of focus is also currently on increasing the efficiency of solar cells. So that's the future perspective. IPCC and all the governments have kind of agreed. So 70% of power by 2050 will come from renewables, mainly from solar PV and wind power, and by 2070 almost 100% of power will be replaced by solar or wind renewable. So currently we have only 20%, as I said, pledged by major economies to reach 100% goal by 2070. So solar, PV, wind, they all will play a major role. Hydro continues to grow. Space it growth historically. We already discussed for nuclear. There is a mixed approach within the society, within the countries, within the community. So march towards the global goal instead of national program. It's more collaborative state effort. Focus on smart grids, energy storage, new materials. Those are the let's say, focus area. So far we talked about electricity. So major part of the total energy use is for electricity. So that's what we talk about now. And that's for the transportation. Here you could see majority of the transportation energy use is within the public, let's say light duty vehicles. And another big share is the fleet transport. And somewhere here is the water transport, air passengers. And where all this energy is coming from. So majority of this is coming from crude oil, basically via gasoline or petrol. And then the heavy distillate, that's the diesel, jet fuel, aviation turbine fuel. Natural gas, compressed natural gas is also. Here you could see which mode of transport is how much polluting. So that's per kilometer, I guess per kilometer per person, and the air transport is somewhere around 255 grams of CO2 emitted. And look at the train compared to 41. So
can you please go back?
yeah, sure. Question?
Flight is taking high risk.
Yes. But intercontinental transport, we can't avoid this mode of transportation. So now, probably you all are already aware, and even in India we have so many EVs nowadays. Countries are already moving from gasoline-based passenger cars to electric vehicles, and here I'm just showing how this rapid growth occurred in last 4 or 5 years. Look at the graph, exponential growth over the last 5 years. And on this front, China is actually leading. So look at the graph or the exponential growth China had compared to some other countries. Once again, electrification country-wise, you could see that's the plug-in electric cars in one per 1,000 people, and here you could see Scandinavian countries are much ahead of others. So rapid growth in last 15 years, but the issue here is capital cost is still higher. So buying an electric vehicle is still 20% more than buying a similar gasoline vehicle. Government subsidies to promote EVs. So even if you can buy a EV here at today with 20% higher cost, the problem with you will be the infrastructure. The range is small and the infrastructure is not there, so you will not find the charging points. It's getting better every day, but still infrastructure is not catching up with the rapid pace of EV sales. Early pushback from auto and oil lobby, they will not, so oil lobby or oil industry for obvious reasons, because they don't want to see their sales dropping down. But unfortunately, in the early phase, auto industry was also not so much interested in moving from gasoline engine to battery operated electric vehicles. But now they are coming up, and a lot of new EV models are coming up. Gasoline technology is a mature technology. That's for all kind of transportation or vehicles. And EV is already matured for light vehicles, but not for heavy duty transportation like truck transportation and other things. So we need different solution for heavy duty sector. Electrification on railway is already one example. So hydrogen biofuel cell maybe it's not a good solution for light vehicles, because the capital cost of buying a hydrogen fuel cell vehicle is almost 2.5 times compared to a gasoline vehicle. Operating this hydrogen vehicle is also 2 times expensive. So operating cost is high, buying cost is high, and on horizon not enough hope or possibility of bringing this cost down. So probably hydrogen for mobility is not a very good solution, especially for light duty vehicles, passenger vehicles. So EVs,
Two-wheelers.
sorry.
Like two-wheelers.
Like two-wheelers, yes.
Because hydrogen buses are there, hydrogen IOCL just.
Yeah, so on the heavy duty
heavy
side,
duties.
it's good, but for the light,
Yeah, but
It's
it's
not
still
so.
on trial because hydrogen refilling stations are still not developed yet.
Yes,
In,
yes.
in Norway also, there are not. What is going on?
many hydrogen
Yeah, HIL.
refueling stations. Yes,
No,
yes. So that's the aspect I touched upon, that the infrastructure is not catching up with the auto industry. So they need to synchronize as well.
Synchronize.
They need to synchronize as well. So we touched upon power industry, we touched upon transportation. Now we look at the industrial consumption. So different form of energy used within the industry. One major is thermal energy. And there we saw it's basically natural gas. So coal is more towards electricity production, but in industrial energy consumption, it's mainly natural gas. Right? So predominantly it's electrical, but also thermal as heat. And electricity, we know, running the pump, running the compressors, and all those kind of uses. Now electrical, we already saw we can replace this electrical energy supply from coal, natural gas to renewable power. So this is already cleaned up. And thermal at various, now thermal energy we need within industry at various temperature levels. So you could imagine if heat is required at lower temperature level, the steam can be generated directly using green electricity, right? But if you need energy at a little bit higher temperature level, you cannot replace it with electricity, because supplying energy at higher temperature level via electricity is much more expensive. So in 20-30 years back, we saw that the efficiency of this thermal power plant was 40%, and that was because of this inherent reason we cannot have condensation within the turbine. And that's why a lot of energy in steam is lost in the condenser. So 20-30 years back, they came up with the idea, especially in Western country where you need a lot of domestic heating. Instead of condensing it in a condenser via cooling water, via cooling tower, they will supply this energy for the district heating. So that's a combined combination of heat and power. They call it CHPs. So you do not waste your energy to atmosphere, but you make useful use in domestic heating, thereby replacing natural gas, which would be used normally to heat up your homes. So at lower temperature, that's easy, but high temperature heat supply, that's a challenge. think this we already all covers. We talked before lunch that cement is an industry where you need to supply a lot of energy because calcination is highly endothermic reaction. A lot of energy needs to be supplied. Another example where you need to supply heat at very high temperature is syngas production, iron industry. So these are the industries where it's absolutely not possible to replace your conventional energy sources like coal, natural gas and others with electricity. We saw the example of cement, CO2 release from process, that's a challenge. So these are hard to abate industry. Limestone calcination is responsible. So if we look at the CO2 emission from a cement plant, almost 70% is coming from limestone and only 30% is from the fuel uses. Although it's very highly endothermic industry reaction, sorry. But 70% is coming from the process side. And as you said, until unless we find a replacement for limestone, we cannot avoid this 65%. And it's highly endothermic, lot of CO2 within the process, and the optimum reaction temperature is also 1400 degrees. That means we can also not replace this energy supply with electricity. So we continue to supply energy via conventional energy sources. This we already. I'm just speeding up because of so questions so far? Questions?
Okay, I have pointed out some things regarding. Okay, all are there, right? Sir very nicely explained about greenhouse gas, greenhouse effect, GHG effect, right? So I think all of you know what is greenhouse. What is greenhouse? House which looks green. Yeah? Greenhouse effect. Greenhouse effect. Yeah, greenhouse effect. Greenhouse effect. Effect coming from the green sources. Greenery. That is the greenhouse effect. Am I correct? Greenhouse effect. It is a far-away process. I mean, greenhouse effect. This is just wanted to clear you all. It doesn't related to greenhouse at all. Greenhouse effect is something which we have plants inside the glass wall. Roof made up of glass. Walls, all the walls made up of glass. Inside there is a plant. Have you